What if I told you that there are black holes so enormous they could swallow our entire solar system without even a burp? These cosmic giants don't just bend the rules of physics, they rewrite them entirely, lurking in the darkness of space with a gravitational pull so intense that not even light can escape their grasp. Imagine something with the mass of billions of suns compressed into a single point, warping the very fabric of reality around it. It sounds like science fiction, but these celestial monsters are very real, and they hold secrets about the universe that we're only beginning to uncover. Think about the scale for a moment. Our sun is enormous. It could fit 1.3 million Earths inside it. Yet, compared to the supermassive black holes at the centers of galaxies, our sun is like a speck of dust next to a mountain. Some of these black holes are so massive that their event horizons, the point of no return, stretch farther than the distance from the sun to Pluto. They don't just influence stars, they command entire galaxies, shaping the motion of billions of stars and determining the fate of cosmic structures we're still struggling to comprehend. Today, we're embarking on a journey to explore 30 astonishing facts about the largest black holes in the universe. We'll uncover how they form, how they grow, and what they can teach us about the nature of space and time itself. From comparisons to everyday objects that make the unimaginable feel tangible, to revelations about their role in the cosmos that will leave you in awe, this is a voyage into the heart of darkness and light. So settle in, open your mind, and get ready to see the universe in a whole new way. To understand these cosmic titans, we first need to define what sets them apart. We often hear the term supermassive, but what does that actually mean? Most black holes are born from the dramatic collapse of a single massive star. These are called stellar mass black holes, and while they are incredibly dense, their size is relatively modest, typically ranging from about 5 to 100 times the mass of our Sun. A supermassive black hole exists on an entirely different scale of existence. These are not the products of a single stellar death, but rather cosmic behemoths that have been gathering mass for billions of years, growing to contain the equivalent of millions or even tens of billions of suns all crushed into a single point. The sheer scale is almost impossible to visualize. Consider our own galactic center, a supermassive black hole named Sagittarius A*. Astronomers have calculated its mass to be a staggering 4 million times that of our Sun. Yet, in the grand hierarchy of these giants, Sagittarius A* is actually quite modest. It's a pebble compared to the mountain that is the black hole at the heart of the galaxy M87, famously photographed in 2019, which tips the scales at a mind-numbing 6.5 billion solar masses. Its event horizon is so vast it could easily engulf our entire solar system. But their immense size isn't their most important feature, it's their profound influence. Unlike their smaller stellar cousins that wander through galaxies, supermassive black holes are nearly always found at the very center of their galactic homes. They act as the ultimate gravitational anchor, the central hub around which an entire galaxy slowly spins. Their incredible gravity dictates the orbits of billions of stars and helps to shape the galaxy itself, influencing its size, structure, and even its future evolution. They are not just inhabitants of galaxies, they are their architects, fundamental engines that drive the life cycle of the cosmos itself. While the supermassive black holes at galactic centers command awe with their sheer scale, the very first black hole ever confirmed was a much smaller stellar mass object, and its discovery story is a brilliant chapter in the history of astronomy. This brings us to our second fact, the identification of Cygnus X-1, the first strong candidate for a black hole, a discovery that fundamentally shifted these objects from theoretical possibility to observable reality. The journey began not with a visual sighting, but with the detection of something invisible, powerful X-rays. In 1964, a team of scientists launched a sounding rocket equipped with special Geiger counters designed to measure high-energy radiation from space. As it soared above Earth's atmosphere, which blocks most X-rays, the instruments picked up an incredibly strong, fluctuating signal from a source in the constellation Cygnus. They named this mysterious emitter Cygnus X-1, marking it as the first X-ray source discovered in that region of the sky. For years, its true nature remained a profound puzzle. What cosmic object could possibly generate such intense and variable X-ray emissions? The key to unlocking this mystery lay in understanding the source of that energy. Scientists theorized that for an object to produce such powerful X-rays, it had to involve the transfer of immense amounts of gravitational energy into heat. The leading hypothesis was a binary system where two objects orbit a common center of gravity. In this model, a visible, massive star would have an incredibly dense, unseen companion. If this companion had a gravitational field strong enough, it could literally pull material gas and stellar wind away from the visible star. This stolen material wouldn't just fall straight down. It would form a superheated, spinning disk of plasma, known as an accretion disk, spiraling inward at velocities approaching the speed of light. The friction and tidal forces within this disk would heat it to millions of degrees, causing it to glow not with visible light, but with the high-energy X-rays that first caught scientists' attention. The hunt was then on to find the visible star that was feeding this hidden monster. After years of painstaking observation, astronomers identified a blue supergiant star known as HD 226868 as the culprit. By carefully tracking its motion, they detected a subtle wobble, revealing that it was indeed locked in a tight orbital dance with an unseen partner. Calculations of the orbital mechanics allowed them to determine the mass of this invisible object. The result was staggering. The companion had to possess a mass roughly 15 times that of our Sun. This presented an insurmountable problem for any other explanation. A neutron star, the other possible remnant of a stellar collapse, has a strict upper mass limit of about 2 to 3 solar masses. Any object more massive than that, yet completely invisible and crammed into such a small area, could only be one thing: a black hole. The confirmation of Cygnus X-1's nature was a watershed moment for astrophysics. It provided the first direct, observational evidence that black holes were not just mathematical curiosities in Einstein's equations, but actual physical objects that could be studied. It validated decades of theoretical work and opened an entirely new window onto the universe, the high-energy universe, where the most violent and energetic processes could be observed. This discovery didn't just find a black hole, it gave birth to a whole new field of observational astronomy, proving that by looking at the universe in different wavelengths of light, we could uncover the secrets hidden in the darkest corners of space. So how do you even begin to measure something you can't see, an object that by its very definition traps all light? Astronomers have developed incredibly clever techniques to do just that, essentially placing these invisible giants on a cosmic scale. The most straightforward method relies on the oldest tool in astronomy, watching things move. Just as we can calculate the mass of the Sun by observing Earth's orbit, we can determine the mass of a black hole by watching the stars and gas that dance around it. The speed and distance of these orbits reveal the gravitational pull at work, and from that, the hidden mass can be precisely calculated with nothing more than Newton's laws of motion. Our own galactic center provides the most stunning example of this. For decades, astronomers have trained powerful telescopes on the heart of the Milky Way, patiently tracking the paths of individual stars swirling around the mysterious radio source known as Sagittarius A**. One star in particular, called S2, has been meticulously followed. It completes a frantic, elliptical orbit in just 16 years, at times screaming past the center at speeds exceeding 3% the speed of light. By mapping its precise path, scientists could perform a brilliant feat of cosmic deduction. The only thing that could possibly hold an object moving that fast in such a tight orbit is an immense concentration of mass. The math revealed an inescapable conclusion: 4 million times the mass of our Sun, crammed into a region smaller than our solar system, confirming the existence of our local supermassive black hole. For black holes that are more distant or shrouded in dust, astronomers turn to other ingenious methods. They study the broad emission lines from the superheated gas in the accretion disk. The width of these spectral lines directly correlates to the speed of the whirling gas. The broader the line, the faster the gas is moving, and the speed of that gas is governed by the mass of the central object it's orbiting. By measuring this Doppler broadening, they can get a reliable estimate of the black hole's mass from the light of its frenzied dinner plate. In the most extreme cases, where a black hole's gravitational influence warps the very fabric of space-time itself, they can use a phenomenon called gravitational lensing. If a black hole passes between us and a distant background star or galaxy, its incredible gravity acts like a lens, bending and magnifying the light from that background object. By carefully analyzing how that light is distorted, scientists can create a map of the gravitational field, and from that, infer the mass of the invisible object causing the distortion. Each of these techniques, from tracing stellar orbits to reading the signatures of stretched light, acts as a separate scale, and when their measurements agree, we can be supremely confident in the staggering weights of these cosmic titans. But if 4 million solar masses sounds immense, and 6.5 billion is almost incomprehensible, then prepare to have your conception of scale completely rewritten. The true giants of the cosmos, known as ultramassive black holes, make even the supermassive ones look almost ordinary by comparison. And the reigning champion, the absolute titan of them all, is an object known as TUN 618. Located an almost unimaginable 10.4 billion light-years away from Earth, TUN 618 is not just a black hole, it is a cosmic superlative. Astronomers have calculated its mass to be a staggering 66 billion times that of our Sun. To even begin to visualize that kind of immensity, consider this. If you were to replace our Sun with TUN 618, its event horizon, its point of no return, would extend far beyond the orbit of Pluto, engulfing our entire solar system, and then continuing outward to swallow the neighboring stars. It is a gravitational abyss of almost mythical proportions. What makes TUN 618 even more spectacular is that it is not a dormant monster. It is an actively feeding black hole, and the evidence of its feast is what allowed us to discover it in the first place. The material spiraling into its clutches forms an accretion disk of such colossal size and ferocity that it shines with the brilliance of 100 trillion suns. This makes TUN 618 one of the most luminous quasars ever observed. A quasar is the incredibly bright, active nucleus of a distant galaxy, powered solely by the gravitational energy of a supermassive black hole. The light from TUN 618's accretion disk is so intense that it outshines every single star in its host galaxy combined. From our vantage point, billions of light-years away, we are essentially seeing the glow from a single dinner plate that is brighter than an entire cosmic city of stars. The existence of such a behemoth so early in the universe's history, we see it as it was 10.4 billion years ago, presents a profound challenge to astrophysicists. Black holes grow by accretion, by slowly pulling in gas and dust and occasionally merging with other black holes. This process takes time. For TUN 618 to have reached 66 billion solar masses so relatively soon after the Big Bang, it forces us to reconsider the very upper limits of black hole growth. It suggests that in the early, dense universe, the conditions must have been perfect for the formation of absolutely monstrous seeds, black holes, that were already supermassive from their very birth, allowing them to balloon to these unbelievable sizes faster than our current models can easily explain. TUN 618 is not just a black hole, It is a cosmic puzzle, a relic from the universe's youth that challenges our understanding of how the most extreme structures come to be. While Ton 618 is a record-breaking titan in terms of pure mass, it is not alone in the pantheon of cosmic giants that push the boundaries of our understanding. Another contender, operating in a far more extreme and violent environment, showcases a different kind of dominance. This brings us to the supermassive black hole at the heart of the Phoenix cluster, a cosmic entity that defies expectations by not only being unimaginably massive but also incredibly active, wielding its power to shape an entire galactic community. The Phoenix cluster itself is a staggering structure, one of the most massive galaxy clusters known in the universe. Think of it not as a single galaxy, but as a vast metropolis of thousands of galaxies all bound together by gravity, swimming in a superheated sea of gas that reaches temperatures of millions of degrees. At the very center of this immense cluster lies its dominant galaxy, and within that galaxy, a supermassive black hole of almost incomprehensible scale, estimated to weigh in at around 20 billion times the mass of our Sun. While slightly smaller than Ton 618, its environment makes its behavior uniquely ferocious and consequential. What truly sets the Phoenix black hole apart is its astonishing level of activity and the profound feedback loop it creates. In most large galaxy clusters, the central supermassive black hole is thought to act as a kind of cosmic regulator. As vast amounts of intergalactic gas cool and flow inward, they feed the black hole, triggering the launch of incredibly powerful jets of energetic particles from its poles. These jets pump energy back into the surrounding gas, reheating it and preventing it from cooling further. This feedback mechanism effectively puts a limit on how many new stars can form, as stars are born from cool gas. It's a balancing act that keeps the galaxy from growing too big, too fast. But the Phoenix black hole seems to be operating on a different set of rules entirely. Here we witness a paradox in action. It is both gluttonously feeding and furiously expelling energy at a rate that is almost off the charts. Observations show that it is in the midst of an incredible feeding frenzy, sucking down surrounding matter at one of the highest rates ever observed for a black hole of its size. This should, according to older models, produce tremendously powerful jets that would shut down star formation across the entire central galaxy. Yet that's not what astronomers see. Instead, they have detected massive filaments of unexpectedly cool gas stretching away from the center gas that is the raw material for new stars. It appears that the black hole's intense activity is both heating and cooling the surrounding medium in a complex cosmic dance. While its jets are indeed powerful, the sheer density of the infalling gas in this extreme cluster seems to be overwhelming them. The jets are unable to punch through effectively and instead are dumping their energy in a more localized way, which somehow allows pockets of gas to cool and collapse. The result is a breathtakingly high rate of star formation, with the central galaxy giving birth to new stars at a rate of about 700 per year. To put that in perspective, our own Milky Way galaxy might form 1 or 2 new stars per year. This black hole is not suppressing star formation. It is inadvertently helping to fuel a stellar baby boom of epic proportions. This makes the Phoenix cluster black hole a living laboratory for studying extreme physics. It shows us that the relationship between a supermassive black hole and its host galaxy is not a simple on-off switch but a complex and dynamic interplay of forces. It challenges the established models of AGN feedback, proving that under the most extreme conditions, the rules can be rewritten. This black hole is more than just a massive object. It is a dominant force of nature, simultaneously an engine of destruction and an unexpected catalyst for creation, governing the life and death of stars across its entire cluster. For centuries, black holes existed as shadowy phantoms in the equations of physicists, inescapable conclusions of theory that we could only infer from their gravitational influence on everything around them. We could weigh them, measure their spin, and listen to the ripples they made in space-time, but the ultimate proof, actually seeing the void itself, remained an impossible dream. That all changed on April 10, 2019, when a team of scientists from the Event Horizon Telescope collaboration held a series of simultaneous press conferences around the globe and unveiled an image that shook the scientific world. The first direct visual evidence of a black hole's shadow, the dark heart of the galaxy Messier 87. This historic image, which looked like a fuzzy, fiery donut of light encircling a central darkness, was not the work of a single, massive telescope. It was the culmination of one of the most ambitious experiments in the history of astronomy. The Event Horizon Telescope, or EHT, is not a physical instrument in one location. Instead, it is a virtual telescope of virtually planetary scale, created by synchronizing a global network of 8 radio observatories, from the high peaks of Hawaii and Arizona to the frigid landscapes of the South Pole and the mountains of Spain and Chile. Using a technique called very long baseline interferometry, these widely separated dishes were pointed at M87's core in perfect unison, effectively combining their power to act as one single Earth-sized radio dish. The resolving power of this virtual instrument is almost beyond belief sharp enough to read a newspaper in New York City from a sidewalk cafe in Paris. They focused this incredible power on a target of almost perfect immensity, the supermassive black hole known as M87*, a monster weighing 6.5 billion times the mass of our Sun. Its enormous size and relative proximity at 55 million light-years away made it one of the largest apparent black holes in the sky, a prime candidate for this first-ever portrait. For over a week in April 2017, every time the weather cooperated at all 8 locations, the EHT collected petabytes of raw data on the radio waves emanating from the black hole's vicinity. This data was so vast it couldn't be sent over the internet. It had to be physically shipped on hundreds of hard drives to supercomputing centers in the United States and Germany, where teams of researchers spent 2 years painstakingly calibrating, processing, and reconstructing it into a final picture. But what are we actually seeing in that now iconic image? That ring of brilliant, asymmetrical light is not the black hole itself. By definition, a black hole emits no light. What we are witnessing is the black hole's silhouette, its shadow, etched onto the incredibly bright, superheated material of its own accretion disk. The intense gravity of M87* bends the very paths of the light photons swirling around it, warping our view into a perfect circle. The reason one side appears dramatically brighter is due to the mind-bending effects of Einstein's special relativity. The side of the disk that is rotating toward us at a significant fraction of light speed has its light boosted, making it appear brighter, while the side spinning away from us has its light dimmed. This dazzling, lopsided ring of light surrounds the central darkness of the event horizon, the point of no return, providing the most direct confirmation possible of their existence. The implications of this single image are monumental. It wasn't just a pretty picture, it was a rigorous scientific measurement that once again put Einstein's theory of general relativity to the test under the most extreme conditions imaginable. The precise size and shape of that shadow matched the predictions of relativity with stunning accuracy, ruling out a host of alternative theories of gravity. It provided visual, tangible proof of the event horizon, that mysterious boundary we had theorized about for so long. This achievement, a testament to human ingenuity and international collaboration, forever moved black holes from the abstract realm of mathematics into the concrete world of observable phenomena, allowing us to literally gaze into the abyss and confirm that the predictions we made about its nature were astonishingly correct. While the image of M87's shadow gave us a face for these cosmic monsters, it only captured a single moment in a black hole's life, a relatively quiet one at that. To witness a supermassive black hole in its most spectacularly violent and energetic state, we must turn our attention to the most powerful persistent engines in the universe, quasars. The term itself, short for quasi-stellar radio source, hints at their initial mystery. When first discovered in the 1950s, they appeared as star-like points of light on photographic plates, but their intense radio emissions revealed they were something entirely alien and unimaginably powerful. A quasar is not the black hole itself, but rather the brilliant signature of a supermassive black hole in the throes of an unimaginable feast. It is the active galactic nucleus of a distant galaxy, shining with a fury that can outshine every single star in that galaxy combined. This phenomenal energy output has a single, simple source, gravity. As colossal amounts of gas, dust, and even entire stars spiral inward toward the event horizon, they don't just vanish quietly. This material forms a vast, chaotic, and incredibly hot accretion disk spinning at nearly the speed of light. The friction and gravitational stresses within this disk heat it to temperatures of millions of degrees, causing it to glow with the intensity of 100 trillion suns across the entire electromagnetic spectrum, from radio waves to gamma rays. The sheer luminosity of a quasar is what makes it visible across cosmological distances, acting as a lighthouse beacon from the early universe. The brightest known quasars can be thousands of times more luminous than a giant galaxy like our Milky Way, all that energy emanating from a region not much larger than our solar system. This concentration of power is almost beyond physics as we know it. For a time, astronomers were baffled about what natural process could possibly generate such staggering amounts of energy from such a small volume of space. The answer, we now know, is the supremely efficient conversion of gravitational energy into radiation by a supermassive black hole. Matter falling into the intense gravity well of a black hole can convert up to 40% of its mass directly into energy, a process orders of magnitude more efficient than nuclear fusion, which powers stars. Beyond their raw power, quasars play a crucial role as cosmic tools, allowing us to probe the conditions of the infant universe. Because light takes time to travel, looking out into the deep universe is equivalent to looking back in time. The most distant quasars we have detected are seen as they were when the universe was less than 1 billion years old. Their very existence at such an early epoch tells us that supermassive black holes were able to form and grow to billions of solar masses incredibly quickly, posing a significant challenge to our models of cosmic evolution. Furthermore, the light from a quasar acts like a flashlight, illuminating everything in its path. As this light travels for billions of years to reach our telescopes, it passes through countless clouds of interstellar and intergalactic gas. These clouds absorb specific wavelengths of light, imprinting a unique barcode onto the quasar's spectrum. By decoding this barcode, astronomers can trace the composition, temperature, density, and evolution of matter throughout cosmic history, using quasars as the brightest background lights in the universe. But the voracious feeding of a supermassive black hole doesn't just result in a brilliant glow. It can also forge the most powerful and focused cannons in the cosmos. While the accretion disk spins in a flat plane around the equator, some of the infalling material, along with immense amounts of energy, is channeled and blasted away from the poles at velocities approaching the speed of light. These are relativistic jets, and they represent one of the most dramatic and energetic processes in the universe, capable of shaping the evolution of entire galaxies. The engine behind these colossal beams is a complex interplay between the black hole's insane gravity, its rapidly spinning accretion disk, and incredibly powerful magnetic fields. As ionized gas plasma spirals inward in the disk, it becomes tangled with magnetic field lines that are themselves twisted and amplified by the disk's furious rotation. These magnetic fields act like a slingshot or a gigantic particle accelerator, funneling a fraction of the superheated material away from the poles of the black hole. Because the rotational axis is the path of least resistance, This material is ejected in two narrow, oppositely directed jets, punching through any surrounding gas and dust with unimaginable force. The effects of these jets are nothing short of apocalyptic on an interstellar scale. As they scream across space for thousands or even millions of light years, they carry with them tremendous energy, plowing into the surrounding intergalactic medium. This interaction heats the diffuse gas that permeates the space between galaxies, preventing it from cooling, collapsing, and forming new stars. This process, known as AGN feedback, is a crucial self-regulating mechanism. The black hole's own feeding frenzy ultimately creates the jets that shut off its future food supply, preventing it from growing indefinitely and explaining why we don't see black holes 1,000 times larger than Ton 618. They are their own ultimate limit. We can observe the spectacular consequences of these jets across the universe. In radio telescope images, we see them as colossal, balloon-like lobes on either side of a galaxy, where the jets have finally slammed to a halt and deposited their energy. These radio lobes can be vastly larger than the galaxy that produced them, sometimes stretching for millions of light years. The energy required to create and sustain these structures is almost beyond calculation, dwarfing the combined output of every star in the galaxy for millions of years. It is a humbling reminder that the supermassive black hole at the center, though hidden in darkness, is often the most dominant and influential force in a galaxy's life, capable of both giving birth to stars through complex feedback and with these immense jets putting a definitive stop to the process. Even as we grapple with the immense scale of Ton 618, the universe presents us with yet another colossus that pushes the boundaries of what we thought was possible. Lying 12 billion light-years away, we find the black hole known as S50014+81, a cosmic entity so vast it is estimated to contain 40 billion times the mass of our Sun. To put that almost incomprehensible number into perspective, its event horizon would have a radius larger than 800 astronomical units. If placed at the center of our solar system, this boundary of no return would extend far beyond the orbit of Pluto, engulfing the Kuiper belt and reaching well into the scattered disk of icy planetesimals at the very edge of the Sun's influence. It is a gravitational titan of almost mythical proportions. What makes S50014+81 particularly fascinating is not just its staggering mass, but its incredible activity and the specific way we observe it. This black hole is not a quiet giant, it is the engine of a hyperluminous blazar. A blazar is a specific type of active galactic nucleus, a cousin to the quasar, but with a crucial and dramatic difference. While the brilliant light of a standard quasar is emitted in all directions, a blazar has one of its powerful, relativistic jets pointed almost directly at Earth. Imagine a cosmic lighthouse where we are positioned perfectly in the path of the blinding beam. This alignment means we are staring directly down the barrel of the most powerful particle accelerator in the universe, receiving a focused, intense barrage of radiation across the entire spectrum, from radio waves to high-energy gamma rays. This direct view makes blazars appear exceptionally bright and violently variable, their light flickering as magnetic storms and shock waves travel along the jet. The sheer luminosity of this object is a direct testament to the ferocious rate at which it is consuming matter. The gravitational energy released as gas and dust spiral into its abyss is so immense that its accretion disk shines with the brightness of over 300 trillion suns. This makes it one of the most luminous single objects ever identified in the cosmos. That light has been traveling through space for 12 billion years to reach us, meaning we are seeing this behemoth as it existed when the universe itself was only about 1.6 billion years old, a mere toddler in cosmic terms. And this is where S50014+81 presents a profound and exciting challenge to astrophysicists. The existence of such a mature, monstrous black hole so early in the universe's history creates a significant puzzle for our models of black hole formation and growth. Black holes are thought to grow through two primary methods: by steadily accreting mass from their surroundings and by merging with other black holes. Both processes take time. For a black hole to reach 40 billion solar masses in just over a billion years, it suggests that the seed from which it grew must have been extraordinarily massive itself. It could not have started as a mere stellar mass black hole from a single supernova. There simply wouldn't have been enough time for it to accumulate such an unbelievable amount of mass. This forces scientists to consider alternative origins, such as the direct collapse of enormous primordial gas clouds in the early, dense universe, forming black hole seeds that were already hundreds of thousands, if not millions, of times the mass of our Sun from their very first moment. S50014 plus 81 stands as a colossal beacon from the distant past, its very existence compelling us to rewrite our theories on how the most extreme structures in the cosmos came to be. This intricate cosmic dance between a supermassive black hole and its host galaxy reveals one of the most profound partnerships in the universe, a symbiotic relationship where the fate of one is inextricably linked to the other. For a long time, astronomers viewed these central black holes as mere inhabitants, perhaps fascinating but ultimately passive features of their galactic homes. The groundbreaking realization was that they are not passengers. They are active regulators, fundamental engines that govern the very evolution of the galaxies they reside in through a powerful process known as feedback. The most dramatic form of this feedback is delivered by the colossal jets we discussed, but the influence is far more nuanced and continuous. Even without visible jets, the energy pouring out from an active black hole's accretion disk in the form of radiation and powerful winds of charged particles washes over the surrounding galaxy. This outpouring of energy heats the vast reservoirs of cold gas that are the raw material for new stars. By preventing this gas from cooling and collapsing under its own gravity, the black hole effectively puts a limit on the galaxy's growth. It acts as a cosmic thermostat, switching on when too much gas flows inward, quenching star formation, and then switching off as the food supply dwindles, allowing the cycle to potentially begin again. This self-regulating mechanism explains why we don't see galaxies growing indefinitely large. The central black hole ensures they don't overeat. The most compelling evidence for this deep connection comes from a startling correlation discovered in the late 1990s. Astronomers found that the mass of a galaxy's central bulge, the dense, spherical collection of stars at its core, is directly proportional to the mass of its supermassive black hole. This is a truly remarkable finding. Think of it this way: a galaxy that has a large central bulge of stars will, with near certainty, host a proportionally massive black hole. A galaxy with a smaller bulge will have a smaller black hole. This correlation is incredibly tight, and it spans galaxies of all types, from majestic spirals to featureless ellipticals. It strongly suggests that the growth of the black hole and the growth of the galactic bulge are not independent events. They are part of the same coordinated process of galactic evolution, happening in lockstep over billions of years. How does this coordination work? The prevailing theory is that major galactic events, like mergers with other galaxies, funnel enormous amounts of gas toward the center. This serves a dual purpose. Some of this gas collapses to form new stars, building up the central bulge. The rest of the gas feeds the ravenous black hole, triggering an active phase. The energy released from this feeding frenzy then blows away or heats up the remaining gas reservoir, shutting down further star formation. The black hole, in its violent outburst, essentially terminates the very era of star building that helped create it. This elegant feedback loop ensures that the black hole mass and the bulge mass remain linked, a silent testament to a billion-year dialogue between a dark heart and its stellar body. This relationship is not just a curious fact, it is a fundamental rule of galactic architecture, proving that even the darkest objects in the cosmos play an essential role in shaping the light. But if black holes are the ultimate cosmic traps from which nothing can escape, then how can they possibly evaporate? This brings us to one of the most mind-bending and brilliant theoretical discoveries in all of physics: Hawking radiation, a concept that forever linked the worlds of general relativity and quantum mechanics and gave black holes a surprising, almost poetic life cycle. For decades, the classical view of a black hole, based on Einstein's theory of general relativity, was absolute. Anything that crosses the event horizon is lost forever. Its mass, and therefore its gravitational pull, could only increase. They were eternal, one-way doors into nothingness. Then, in 1974, Stephen Hawking introduced a revolutionary idea that turned this notion on its head by applying the strange rules of quantum mechanics to the edge of the abyss. The key to understanding Hawking's insight lies in the nature of empty space. According to quantum field theory, a vacuum is not truly empty. Instead, it is a seething, bubbling foam of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence from the energy of the vacuum itself, borrowing energy from nothing for an unimaginably brief moment before they almost immediately collide and annihilate each other, paying back the energy debt and vanishing. This constant, frantic creation and destruction is happening everywhere all the time, and we have experimental evidence that proves it's real. Now, imagine this quantum frenzy happening right at the very precipice of a black hole's event horizon. In most of space, these virtual pairs vanish without a trace. But at the event horizon, the extreme gravity creates a dramatic scenario. It's possible for one particle in the pair to fall across the event horizon while its partner escapes into space. The particle that falls in has negative energy, which effectively reduces the mass of the black hole by a tiny, tiny amount. Its partner, now severed from its other half and unable to annihilate, becomes a real particle and flies away from the black hole as genuine radiation. To an outside observer, it appears as if the black hole itself is emitting a faint glow of particles. This is Hawking radiation. The black hole isn't emitting anything from beyond the event horizon. Rather, the radiation is generated outside the horizon by this bizarre quantum process, and the cost of that creation is a slow, steady leak of the black hole's mass. The implications of this are staggering. It means that black holes are not permanent fixtures of the universe. Over time, they lose mass, and as they lose mass, they actually emit radiation faster and faster. For a supermassive black hole like Sagittarius or Asterisk, the rate of evaporation is so incredibly slow that it is completely negligible compared to the mass it gains from absorbing cosmic background radiation and the occasional star. The Hawking radiation temperature for such a giant is far colder than the background temperature of the universe, but for a much smaller black hole, the story is very different. The smaller a black hole is, the hotter its event horizon is, and the more intensely it radiates. A black hole with the mass of a small asteroid would be emitting radiation at a tremendous rate, glowing white-hot and living on a borrowed timescale. It would eventually evaporate completely, and in its final moments, it would unleash a colossal burst of energy equivalent to 1,000,001 megaton hydrogen bombs exploding at once. This theoretical evaporation process presents a profound puzzle known as the black hole information paradox. In quantum mechanics, information is never lost. The state of a system can always, in theory, be reversed. But if a black hole forms from a specific collection of matter, a star with a unique composition, perhaps even a spaceship, and then completely evaporates into a featureless shower of Hawking radiation, what happened to all that specific information about what fell in? It appears to be irretrievably lost, violating a fundamental principle of quantum theory. Resolving this paradox is one of the biggest unsolved problems in theoretical physics, forcing physicists to question our understanding of gravity, quantum mechanics, and the very nature of reality at the most fundamental level. Hawking radiation didn't just give black holes an end. It opened a doorway to a deeper universe of questions we are still striving to answer. For all our focus on the stellar mass black holes born from dying stars and the supermassive behemoths ruling galactic centers, a crucial middle child has long been missing from the black hole family portrait. These are the intermediate mass black holes, a hypothesized class ranging from roughly 100 to 100,000 times the mass of our Sun. They represent a critical evolutionary link, the potential seeds from which the supermassive giants like Cygnus X-1 could have grown. Yet for decades, finding conclusive proof of their existence proved to be one of astronomy's most stubborn challenges. The hunt for these elusive objects has largely centered on two promising cosmic environments. The first are dense, ancient star clusters known as globular clusters. These spherical swarms, which orbit the halos of galaxies like our Milky Way, contain hundreds of thousands of stars crammed into a relatively tiny volume of space. In such a crowded neighborhood, gravitational interactions are frequent and violent. Astronomers theorize that over billions of years, repeated collisions and mergers between stellar mass black holes could eventually build up an intermediate mass black hole at the cluster's very heart. Finding one, however, meant looking for the subtle gravitational sway it would exert on the surrounding stars. After years of painstaking observation, some of the most compelling evidence emerged from a cluster called Omega Centauri. By meticulously tracking the velocities of stars near its core, scientists noticed they were moving far too quickly, their speeds implying the presence of a hidden, dense mass of around 40,000 suns. This is far too heavy to be any collection of stellar remnants and strongly points to a single, intermediate mass black hole holding court at the center. The second line of evidence comes from the detection of mysterious, incredibly bright objects known as ultra-luminous X-ray sources, or ULXS. These are spots within galaxies that emit staggering amounts of X-ray energy, often far from the galactic center, ruling out a supermassive black hole as the source. For a long time, the leading theory was that these were simply stellar mass black holes in binary systems, feeding at an unusually high rate. But there's a fundamental limit, known as the Eddington limit, to how brightly an object of a given mass can shine before the pressure of its own radiation blows away the material trying to feed it. Many of these ULXS were shining hundreds or even thousands of times brighter than the Eddington limit for a typical stellar mass black hole. This left two exciting possibilities. Either we were witnessing a stellar black hole breaking the known laws of physics by super-Eddington accretion, or the engine was simply more massive, requiring a higher Eddington limit. For several of these hyperluminous sources, the math pointed persuasively toward an intermediate mass black hole as the power plant, its greater gravity allowing it to consume matter and shine with a ferocity its smaller cousins could never achieve. Confirming the existence of this intermediate class is about more than just completing a cosmic checklist. It directly addresses one of the biggest unanswered questions in modern astrophysics. How did the supermassive black holes get so big so fast? If the first black holes formed from the collapse of the very first stars, they would have been relatively small, perhaps a few hundred solar masses at most. Growing one of those into a billion solar mass quasar in less than a billion years is a tremendous challenge, like trying to grow a redwood tree from a sapling overnight. Intermediate mass black holes provide a perfect solution. They could have served as the massive seeds that got a head start on growth, either through those early star cluster mergers or perhaps from the direct collapse of enormous primordial gas clouds in the infant universe. Finding them today is like finding a living fossil, a snapshot of the building blocks that eventually assembled the cosmic titans we see at the hearts of galaxies today, finally filling in the missing chapter of the black hole growth story. But all these methods of observing black holes, from studying their feeding habits to capturing their shadow, rely on the light emitted by the matter around them. What if we could instead listen to the universe, to hear the very fabric of reality itself ring like a bell from the most violent collisions imaginable? This incredible possibility became a reality in 2015, when the LIGO Observatory made the first ever direct detection of gravitational waves, ripples in space-time caused by the merging of two black holes over 1.3 billion light-years away. To understand these waves, we need to go back to Einstein's vision of gravity. He proposed that space and time are not a static stage upon which the universe plays out, but a flexible, four-dimensional fabric called spacetime. Imagine stretching a taut rubber sheet. This is our spacetime. When you place a heavy object like a bowling ball on that sheet, it creates a deep dimple. This is gravity, the warping of spacetime by mass. A black hole with its unimaginable density creates the deepest possible dimple, a well so profound that its sides become vertical. Now imagine two such bowling balls orbiting each other on this sheet. As they spiral inward, their motion sends ripples racing outward across the rubber surface. These ripples are gravitational waves traveling distortions in the very geometry of spacetime itself, compressing and stretching everything in their path as they pass through at the speed of light. The event that LIGO detected was the final death spiral of two stellar mass black holes, one about 36 times the mass of our Sun, the other 29. For millions of years, they had been orbiting each other, losing energy in the form of these gravitational waves, drawing inexorably closer. In their final seconds, they reached a significant fraction of the speed of light, whirling around each other hundreds of times per second before finally colliding and merging into a single, more massive black hole of 62 solar masses. In that cataclysmic merger, an amount of energy equivalent to 3 times the mass of our Sun was converted into pure gravitational wave energy and blasted across the universe in all directions. For a brief moment, the merger outshone every star in the observable universe combined, not in light but in gravitational power. The detection of this signal, a faint chirp that rose in frequency and amplitude before abruptly cutting off, was a triumph of human ingenuity. The LIGO observatories and their European counterpart Virgo are not telescopes in any conventional sense. They are the most precise measuring instruments ever built, consisting of 2 immense multi-kilometer long vacuum tubes arranged in an L shape. A laser beam is split and sent down each arm, bouncing off mirrors to travel back and forth before being recombined. In normal circumstances, the light waves cancel each other out. But when a gravitational wave passes through Earth, it minutely warps space itself, making one arm imperceptibly longer and the other shorter for a fraction of a second. This changes the laser travel time, causing the light waves to fall out of sync and create a flicker of light at the detector. The change in length LIGO measures is almost absurdly small, 1/10,000th the diameter of a proton. Detecting that is like measuring the distance to the nearest star to the precision of a human hair. Each collision tells a detailed story. The specific shape and frequency of the gravitational wave signal is a rich data stream that allows scientists to calculate the masses of the black holes involved, their spins, and even the orientation of their orbits. This has opened up an entirely new field of astronomy, allowing us to take a census of black holes that are completely dark, isolated from any stars or gas to give away their presence. We are now hearing the otherwise silent population of black holes across the cosmos. These observations have already revealed black holes of masses we didn't expect to be common, challenging our models of how massive stars live and die. They have provided evidence for black holes spinning in misaligned ways, hinting at chaotic and dynamic formation histories. Every new chirp from the darkness adds another data point, helping us to finally understand the hidden lives and deaths of these dark objects, all by listening to the echoes of spacetime itself. This idea that information is permanently erased from the universe strikes at the very heart of quantum mechanics, which is built on the unshakable principle that information is never truly lost. In the quantum world, the universe is fundamentally predictable. If you know the complete quantum state of a system, the position, momentum, and other properties of every particle at any given moment, the laws of physics should, in theory, allow you to calculate its entire past and future. The information about what something was made of is always preserved, even if it's transformed. You could burn a book to ashes, and while it would be practically impossible, the laws of quantum mechanics state that the information contained in the arrangement of its atoms is still present, however scrambled, in the smoke and the ashes. The universe, at its core, keeps perfect records. Hawking's revelation suggested that black holes were the ultimate cosmic vandals, tearing out the pages of the universe's book and setting them on fire. For decades, this created a deep and troubling schism in theoretical physics, a conflict now famously known as the black hole information paradox. On one side stood the elegant, deterministic rules of quantum mechanics. On the other stood the brutal, one-way street of general relativity's black holes. Most physicists, including Hawking himself for a time, believed one of these two pillars of modern physics must be wrong. The debate was not just academic, it was a battle for the soul of reality, a quest to determine if the universe operates on knowable, consistent rules, or if there exists a fundamental sinkhole of chaos where those rules break down forever. In a stunning turn of events, Stephen Hawking himself eventually changed his mind. In 2004, nearly 30 years after first proposing his radiation theory, he conceded a famous bet to physicist John Preskill, admitting that information must in fact escape a black hole. But how, if nothing can climb out of the gravitational pit, how can the information about what fell in get out? This is where modern theoretical physics enters a realm of almost science-fictional wonder, proposing solutions that radically reshape our understanding of reality. One of the most profound and popular resolutions is the holographic principle. This mind-bending idea suggests that all the information that falls into a black hole is not lost inside its three-dimensional volume, but is instead encoded on its two-dimensional event horizon, the surface boundary. Think of it like a cosmic piece of holographic film. A standard hologram is a two-dimensional surface that, when lit correctly, projects a fully three-dimensional image. The holographic principle applies this concept to the entire universe, proposing that our perception of a three-dimensional reality might be a projection from information stored on a distant two-dimensional surface. For a black hole, this means every particle, every bit of energy that crosses the horizon leaves an imprint, a tiny change or bit of information on the surface of the event horizon. As the Hawking radiation evaporates the black hole, this radiation is not random. It carries away that encoded information, slowly and faithfully transmitting the story of what fell in back out into the universe. The black hole, in its final moments of evaporation, would effectively tell its entire life story through its radiation. An even more dramatic and violent proposed solution is the black hole firewall hypothesis. If the holographic principle is a gentle, information-preserving data transfer, the firewall is a cataclysmic fail-safe. This theory suggests that the event horizon is not the smooth, uneventful space that general relativity predicts. Instead, it might be a searing wall of unimaginably high energy particles, a literal firewall that would instantly incinerate anything that crosses it. The need for this drastic idea arises from trying to reconcile the experiences of two different observers. To someone falling into a black hole, crossing the event horizon should be uneventful due to the principle of equivalence in general relativity. But from the quantum perspective, in order for the information to be preserved and encoded on the horizon for the outside universe, an infalling object must interact with the horizon in a tremendously energetic way. The firewall is the proposed result of this conflict, a desperate measure by the laws of physics to prevent a contradiction, ensuring information is not lost by dramatically altering the nature of the horizon itself. An object wouldn't quietly fall in, it would collide with a wall of fire, its information being scattered onto the horizon in the resulting energy blast. These ideas push the boundaries of our comprehension, forcing us to consider that our classical notions of space, time, and information are profoundly incomplete. The resolution to the information paradox likely lies in a theory of quantum gravity, a yet-to-be-discovered framework that seamlessly merges the large-scale warping of space-time with the tiny, probabilistic world of quantum particles. Whether the answer is a holographic universe, a fiery boundary, or something even more exotic, the paradox stands as a brilliant beacon, guiding physicists toward a deeper, more unified understanding of the cosmos, proving that even the darkest objects in the universe can illuminate our greatest truth. Now we arrive at one of the greatest and most pressing mysteries in all of modern astrophysics. If growing a supermassive black hole takes billions of years through steady accretion, how on earth did we end up with quasars like TUN 618 and S50014+81 shining with the light of 100 trillion suns when the universe was less than a billion years old? It's a cosmic timing problem of epic proportions, and the most promising solution lies in the nature of the seeds from which these giants grew. The prevailing theory is that the first supermassive black holes didn't start small. They were born big, emerging from the primordial chaos of the early universe as ready-made heavyweights. One of the leading hypotheses for creating these massive seeds is a process known as direct collapse. In the first few 100 million years after the Big Bang, the universe was a much denser, simpler place, filled with vast clouds of pure hydrogen and helium gas. Under the right conditions, a particularly massive and stable cloud could have begun to collapse under its own immense weight. But there was a catch. For it to form a black hole directly, it had to avoid fragmenting into thousands of smaller clouds that would birth individual stars. The key to preventing this fragmentation was a lack of elements heavier than helium, which astronomers call metals. These metals act as efficient coolants, allowing gas to lose heat and condense into stars. Without them, the gas cloud stays hot and puffy, resisting breakup. Such a pristine, massive cloud could then collapse in a single, catastrophic event, bypassing the star formation stage entirely and crumpling directly into a black hole with a starting mass of anywhere from 10,000 to 100,000 times that of our Sun. This gives the resulting black hole a colossal head start, a massive seed perfectly positioned to gorge on the abundant surrounding gas and rocket to supermassive status in a relatively short amount of cosmic time. A second, and perhaps more traditional, theory points to the first generation of stars, known as population 3 stars. These would have been the universe's very first luminaries, forming from the pristine hydrogen and helium with no heavier elements to regulate their size. Theorists believe these stars could have been monsters, hundreds of times more massive than our Sun. A star that massive lives a spectacularly short and violent life, burning through its nuclear fuel in just a few million years before exploding in a cataclysmic hypernova or collapsing directly without a supernova. The remnant left behind would be a black hole of perhaps a few hundred solar masses. While significantly smaller than a direct collapse black hole, these stellar mass seeds could then grow through a frantic combination of rapid accretion and frequent mergers with other black holes in the dense, crowded environments of the first proto-galaxies. In this scenario, it's a race against time, building a giant through a frantic series of cosmic mergers and acquisitions. The most compelling evidence for these theories doesn't come from finding the seeds themselves, which is currently beyond our technological reach, but from observing the fully grown giants they must have produced. The existence of those incredibly luminous, high redshift quasars we discussed is the ultimate smoking gun. When we detect a quasar that is billions of times the mass of the Sun, at a time when the universe was only 7% of its current age, we are essentially looking back at the end result of this seeding process. The light from these objects has been traveling for over 13 billion years to reach us, providing a snapshot of a black hole that had to have been already enormous almost immediately after the dawn of time. Their mere presence forces us to accept that the early universe was a place of extreme physics, where black holes could form at masses we simply don't see in the local, modern universe, and where they could accrete matter at rates pushing the very limits of physics, in a special era when gas was plentiful and the regulatory mechanisms of later galaxies did not yet exist. Each of these distant, brilliant beacons is a powerful argument that the seeds of today's cosmic titans were planted in the unique and fertile soil of the cosmos's infancy. We've seen how black holes can grow to unbelievable sizes and unleash unimaginable power, but mass isn't their only defining feature. These cosmic objects can also possess a property that makes them even more dynamic and strange: rotation. Much like a spinning skater pulling their arms in to accelerate, a black hole can spin at a significant fraction of the speed of light, and this rotation doesn't just affect the black hole itself. It warps the very fabric of the universe around it in a phenomenon so bizarre it had to be predicted by Einstein himself. This mind-bending effect is known as frame dragging. According to general relativity, mass tells spacetime how to curve, and that curved spacetime tells objects how to move. This is what we experience as gravity. But when a massive object also rotates, it adds a new twist to the equation, quite literally. The rotation pulls the surrounding spacetime into a vortex, forcing it to circle around the spinning mass. Imagine a bowling ball spinning in a thick fluid like honey. The fluid closest to the ball would be dragged around with it. For a spinning black hole, the fluid is spacetime itself. Anything that comes near light, dust, even entire stars, is compelled to move in the direction of the spin, caught in a cosmic whirlpool from which there is no escape. The effect is most extreme just outside the event horizon in a region called the ergosphere, where space is being dragged around so forcefully that it becomes impossible for any object to remain stationary. You would be swept along by the current of twisting spacetime, a helpless raft on a relativistic river. Measuring something as abstract as the spin of an object we can't see requires another stroke of astronomical genius, and the key lies once again in the brilliant light of the accretion disk. As matter spirals inward toward a spinning black hole, it follows the flow of this dragged spacetime, eventually settling into a stable orbit. The radius of this innermost stable circular orbit is directly determined by the black hole's spin. For a static black hole that isn't spinning, this orbit is fairly large. But for a black hole that's rotating rapidly, the dragging of spacetime is so powerful that it pulls matter in much closer, like a whirlpool sucking debris toward its center. The closer matter can get, the faster it orbits and the hotter it becomes, emitting higher energy radiation. This is where X-ray astronomy comes in. By pointing space-based telescopes like NASA's Chandra X-ray Observatory or New Star at an active black hole, scientists can analyze the spectrum of light coming from its inner accretion disk. The superheated iron atoms in this disk emit X-rays at a very specific energy, but this light is distorted by the insane gravitational forces and the incredible speeds involved. The black hole's gravity stretches the light to longer wavelengths, a process called gravitational redshift, while the Doppler effect from the orbiting gas blueshifts light from material moving toward us and redshifts light from material moving away. For a rapidly spinning black hole with a very small inner orbit, these effects are extreme, smearing the sharp iron emission line into a broad, skewed hump. By carefully modeling the precise shape of this distorted line, astrophysicists can work backward to calculate the size of that innermost orbit and from that determine the black hole's spin. One of the most spectacular examples of this is a stellar mass black hole system located about 35,000 light-years away in the constellation Aquila, known as Jubres 1915+105. This system is a microquasar, a small-scale version of the brilliant quasars powered by supermassive black holes. It consists of a regular star and a black hole about 10 times the mass of our Sun, locked in a tight orbit. What makes this object so remarkable is its spin. By analyzing the X-rays from its accretion disk, astronomers have determined that this black hole is rotating at an astonishing speed, at more than 90% of the maximum rate allowed by the laws of physics. It's whipping around so fast that its event horizon is not a perfect sphere but is flattened at the poles, and the space-time around it is a frenzied maelstrom. The energy extracted from this furious rotation is thought to power the colossal superluminal jets that this system is famous for, blasting material out at over 90% of the speed of light. GRS 1915+105 stands as a stunning laboratory for testing the limits of physics, a testament to how a simple property like spin can transform a black hole into one of the most energetic and dynamic engines in the entire cosmos. While the title of the absolute largest black hole belongs to distant titans like Ton 618, the reigning champion within our own cosmic neighborhood, and certainly the most famous, is the magnificent beast at the heart of Messier 87. This is the black hole we now know intimately as M87*, the very first one humanity ever laid eyes on, and it remains an unparalleled natural laboratory for probing the most extreme physics in the universe. Its sheer immensity is the first thing that commands awe, tipping the scales at 6.5 billion times the mass of our Sun. M87* is a gravitational anchor of almost incomprehensible scale. To put that into a tangible perspective, its event horizon stretches over 20 billion kilometers across. If you were to place this black hole at the center of our solar system, that boundary of no return would extend far beyond the orbit of Pluto, completely engulfing the Kuiper belt and reaching into the scattered disk at the very edge of the Sun's influence. The entire planetary system we call home would simply vanish inside it. This is the scale of the monster we are dealing with, and it's right next door on the cosmic scale, a mere 55 million light-years away. But M87* is far more than just a massive, dark pit. It is an incredibly dynamic and active engine, and its most spectacular and visible feature is a colossal jet of superheated plasma that blasts out from its core, stretching for an astonishing 5,000 light-years into intergalactic space. This jet is a direct consequence of the black hole's immense power and rapid spin. Not all the material drawn toward the event horizon actually falls in. Some of it, along with a tremendous amount of energy, is captured and accelerated by incredibly powerful magnetic fields that are twisted tightly by the black hole's rotation. This material is then funneled and launched outward at nearly the speed of light from the poles, creating a narrow, focused beam of matter and radiation that punches through the surrounding gas of the galaxy. We are fortunate to have a nearly perfect view of this jet from Earth, seeing it at a slight angle that allows us to study its structure in incredible detail. Observations show it's not a smooth stream but a knotted, superluminal chain of brilliant blobs, regions where shock waves traveling down the jet compress particles and cause them to shine with intense synchrotron radiation across the entire electromagnetic spectrum. This proximity and activity are what make M87* such a priceless cosmic laboratory. That first historic image from the Event Horizon Telescope was not just a one-off achievement, it was the beginning of a new era of observation. Scientists are now creating movies of the gas swirling around its event horizon, watching how the structure of that fiery ring of light changes over time. This allows them to test the predictions of general relativity with a precision never before possible, observing firsthand how light and matter behave in an environment where gravity is so strong it warps the very paths that photons travel. They can study the mechanics of accretion, how the black hole feeds, and the launch mechanism of its gigantic jet in real time, something impossible to do with the more distant quasars. Furthermore, by combining the EHT image with data from other telescopes observing the much larger jet, astronomers can connect the events happening at the very precipice of the event horizon with the enormous consequences millions of times farther out. It's like simultaneously studying the spark inside an engine cylinder and the movement of the entire car, understanding how the tiny, fundamental physics translates into massive cosmic scale results. M87* is a gift that keeps on giving, a unique natural experiment that allows us to stress test our theories of gravity, magnetohydrodynamics, and particle acceleration under conditions that we could never hope to replicate on Earth, providing a window into the fundamental laws that govern the entire universe. But for all the power and presence of these supermassive giants, they still only account for a small fraction of the total matter in the universe. The vast majority, about 85%, is something entirely different and far more mysterious: dark matter. This invisible substance doesn't emit, absorb, or reflect any light, revealing its presence only through its gravitational pull on galaxies and galaxy clusters. For decades, these two cosmic mysteries, black holes and dark matter, were studied as separate puzzles. But what if they are deeply connected? Some of the most fascinating theories in modern astrophysics suggest that the answers to one might be found by studying the other. One of the most compelling ideas is that a significant portion of dark matter could actually be made of black holes, but not the kind we've been discussing. These would be primordial black holes, theorized to have formed not from the death of stars, but in the incredibly dense, frenetic environment of the very early universe, mere fractions of a second after the Big Bang. Tiny fluctuations in density could have caused pockets of space to collapse directly into black holes with a wide range of masses. Unlike stellar mass black holes, these primordial ones could be almost any size, from smaller than a pinhead to many times the mass of our Sun. If vast numbers of these ancient objects were forged in the first moment of time, they could be drifting unseen throughout every galaxy and in the vast voids between them, their collective gravity providing the missing mass we call dark matter. This idea elegantly solves two problems at once, but it also faces significant challenges. The theory requires a specific population of primordial black holes, likely within a certain mass range, to avoid conflicting with other observations. For instance, if too many primordial black holes with the mass of an asteroid existed, they would frequently pass through our solar system, and their gravitational microlensing effects would have been detected by now as they bent the light of distant stars. Similarly, if they were too massive, their influence on the delicate structure of the earliest light in the universe, the cosmic microwave background, would be noticeable. So while the possibility remains open for a specific population of primordial black holes to account for some dark matter, it's unlikely they can explain all of it. The hunt for these elusive relics is ongoing, and their discovery would revolutionize our understanding of both the universe's birth and its hidden architecture. Beyond being dark matter itself, black holes could also act as unique laboratories for detecting it. Imagine a black hole moving through a halo of dark matter particles. While dark matter doesn't interact electromagnetically, meaning it doesn't form accretion disks and shine, it does feel gravity. Theoretical models suggest that dark matter particles could be captured by a black hole's gravity, building up in a dense cloud around it. The interactions within this cloud could eventually lead to the dark matter annihilating with itself, producing a flash of gamma rays that we could potentially detect. This would give us an indirect way to see the dark matter by observing the very black holes it surrounds. Furthermore, the presence of this dark matter halo could subtly influence the black hole's growth and even its spin over billions of years, leaving an imprint that astronomers could search for in the data from gravitational wave observatories. Perhaps the most significant connection lies at the very heart of galaxies. We know supermassive black holes and dark matter halos coexist in galactic centers, and their gravitational influences are deeply intertwined. Some models suggest that the incredible density of dark matter at the core of a galaxy could actually fuel and accelerate the growth of the central black hole. As dark matter particles orbit, they can have their paths altered by the black hole's gravity, losing energy and spiraling inward to be consumed. This process could provide a steady, invisible food source for the black hole, helping it to reach supermassive sizes faster than models that only account for normal matter accretion. This dark matter diet could be a crucial piece of the puzzle, explaining how the earliest quasars grew to such staggering sizes in such a short time after the Big Bang. The dance between the visible darkness of the black hole and the invisible darkness of the matter surrounding it may be the key to understanding the formation of the universe's largest structures. While the relativistic jets and steady glow of quasars represent the black hole's continuous feast, there are moments of far more violent and spectacular consumption, cosmic events of unimaginable fury that illuminate the darkness for a brief, brilliant moment. These are tidal disruption events, one of the most extreme phenomena in the universe, occurring when a star's orbit brings it perilously close to a supermassive black hole. The star, in a literal sense, meets its maker in the most dramatic way possible, shredded into a stream of gas by the black hole's overwhelming gravity. The destructive process is driven by a simple but brutal principle, a difference in gravitational pull known as a tidal force. We experience a mild version of this on Earth, where the Moon's gravity pulls more strongly on the side of our planet facing it, creating the ocean tides. For a star approaching a black hole, this difference becomes catastrophic. The side of the star closest to the black hole feels a vastly stronger gravitational pull than the side farthest away. This creates an immense stretching force, pulling the star apart horizontally while simultaneously compressing it vertically. Once the star crosses a critical boundary known as the tidal radius, where the black hole's tidal forces exceed the star's own gravity holding it together, it can no longer maintain its integrity. It is, quite literally, spaghettified, stretched into a long, thin stream of hot gas in a process that can take just a few hours. What follows this stellar demolition is a breathtaking cosmic fireworks display. The stream of stellar debris doesn't all fall directly into the black hole at once. About half of it is ejected out of the system entirely, flung away at incredible speeds. The other half remains bound to the black hole, but it doesn't form a neat, orderly disk immediately. The various strands of gas, all on different orbits, collide with each other in a chaotic frenzy. This collision converts their immense orbital energy into heat, causing the gas to glow with a ferocious intensity, creating a sudden, brilliant flare of light that can outshine every star in its host galaxy combined. This flare peaks in the ultraviolet and X-ray parts of the spectrum, a telltale signature of matter heated to millions of degrees. For a period of months or even years, astronomers can watch as this luminous aftermath slowly decays, as the gas finally settles into a more stable accretion disk and is steadily consumed by the black hole. These cataclysmic events are far more than just a spectacular light show. They are invaluable scientific tools. For astronomers, a tidal disruption event is like a controlled experiment conducted on a galactic scale, offering a rare opportunity to study an otherwise dormant black hole. The vast majority of supermassive black holes in the universe are quiet, not actively feeding and therefore not emitting the bright radiation that makes them easy to find. A tidal disruption event suddenly switches one on, flagging its location and revealing its presence. By analyzing the light curve of the flare, how quickly it brightens and how slowly it fades, scientists can accurately estimate the mass of the central black hole. The duration and evolution of the event are directly tied to the gravity of the destroyer. Furthermore, the detailed spectrum of the emitted light acts as a forensic report on the devoured star. By dissecting this light, astronomers can determine the composition of the star, revealing whether it was rich in hydrogen, helium, or heavier elements. This provides a unique census of the stellar population right at the galactic center, an environment that is normally too crowded and dusty to observe individual stars clearly. Each tidal disruption event is a fleeting but incredibly rich source of data, a single moment of destructive creation that lays bare the properties of both the victim and the predator, giving us a front-row seat to the violent physics at the edge of oblivion. Imagine an object of unimaginable complexity falling into a black hole, a library of books, a supercomputer, an entire planet teeming with unique structures and life. According to one of the most elegant and yet most troubling principles in theoretical physics, all of that intricate information, every last detail, is seemingly erased from the universe forever. The black hole that consumes it will be, for all intents and purposes, identical to one that formed from a simple cloud of pure hydrogen gas of the same mass. This is the essence of the infamous no-hair theorem, a concept that reduces the most complex objects in existence to their most basic, minimalist description. The theorem gets its peculiar name from a playful metaphor. A black hole has no hair, meaning no fussy, detailed features or complicated external frills. In the stark, clean world of classical general relativity, a black hole can be completely and uniquely described by just three, and only three, observable parameters: its mass, its electric charge, and its angular momentum or spin. Everything else about whatever fell in its chemical composition, its atomic structure, whether it was made of matter or antimatter, the pattern of continents on a planet, the words in a book, is irretrievably lost behind the event horizon. The black hole, in effect, gets a radical haircut, shedding all distinguishing information until it is bald, smooth, and characterized by nothing but these three numbers. This incredible simplification arises directly from the nature of the event horizon itself. Think of it as the ultimate cosmic blender and eraser. The gravitational forces at play are so extreme that any structure or complexity in the infalling matter is completely and utterly destroyed. Atoms, molecules, and even the very concept of solid matter cease to have any meaning. The matter is compressed into a featureless soup of its most fundamental constituents, adding only to the total mass, and any net electric charge or overall rotation is imparted to the black hole as a whole. The result is a perfect, smooth, and utterly simple object. If you were to somehow measure the mass, charge, and spin of a black hole from a safe distance, you would know everything there is to know about it. It doesn't have a rocky surface, a metallic core, or a northern hemisphere. It is pure gravity distilled into its simplest possible form. For physicists, this theorem is both a thing of beauty and a source of deep existential dread. Its beauty lies in its stunning simplicity, a rare case in the messy universe where complexity is boiled away to reveal a few fundamental truths. It is a powerful tool for theorists, allowing them to model and understand black holes without getting bogged down in an infinite number of possible details. Yet, this same simplicity creates a direct and violent collision with the other pillar of modern physics, quantum mechanics. In the quantum world, information is sacred. The fundamental laws are unitary, meaning information is never truly destroyed. It can be scrambled, transformed, or hidden, but it must be preserved in principle. If you knew the exact quantum state of every particle in the smoke and ashes of a burned book, you could, in theory, reverse the process and reconstruct the book. The no-hair theorem suggests that black holes are the ultimate exception to this rule, that they are the one place in the universe where information is not just scrambled but permanently annihilated. This is the heart of the black hole information paradox, a conflict that has driven theoretical physics forward for decades. The ongoing debate over this paradox is where things get truly fascinating. The resolution likely lies in a concept that pushes the boundaries of our imagination, the holographic principle. This mind-bending idea suggests that all the information about what fell into the black hole is not actually lost inside its three-dimensional volume. Instead, it is precisely encoded on its two-dimensional event horizon, the surface boundary. Think of it like a cosmic piece of holographic film where a two-dimensional surface contains all the information needed to describe a three-dimensional object. In this view, the information is never truly inside the black hole. It is smeared across its surface in tiny, Planck-length pixels. As the black hole evaporates through Hawking radiation, this theory suggests the radiation is not random but carries away that encoded information, slowly and faithfully transmitting the story of what fell in back out into the universe. The black hole's hair, in the most exotic way imaginable, might not be gone after all. It might just be painted onto a surface we are only beginning to learn how to read. Now, if the no-hair theorem tells us black holes are the simplest objects in the universe, a discovery in the 1970s revealed they might also be the most chaotic and disordered systems imaginable, a paradox that led to a revolutionary new field of physics. This brings us to a profound connection between the darkest objects in space and one of the most fundamental concepts in all of science, entropy. At its heart, entropy is a measure of disorder, a count of the number of ways the microscopic components of a system can be arranged while still looking the same from the outside. A tidy room has low entropy, a messy room has high entropy. The second law of thermodynamics states that the total entropy of a closed system always increases over time. The universe tends toward messiness. For decades, black holes were the ultimate affront to this law. If you could throw a high-entropy object, like a box of gas with its trillions of atoms in disarray, into a black hole, it would simply vanish. The universe's total entropy would appear to decrease, violating a foundational pillar of physics. The brilliant solution to this paradox came from a young physicist named Jacob Bekenstein, advised by the legendary John Wheeler. Bekenstein proposed a radical idea. What if the black hole itself carries entropy, and not just a little bit, but an immense amount of it? He suggested that a black hole's entropy is not proportional to its volume, as it is for a normal three-dimensional object, but to the area of its event horizon. This was a completely counterintuitive notion. The surface area, not the volume, defines how much disorder is contained within. Stephen Hawking initially disagreed, arguing that if a black hole had entropy, it must also have a temperature, and anything with a temperature must emit radiation. And everyone knew nothing could escape a black hole. Hawking set out to prove Bekenstein wrong, but ended up doing the exact opposite, making one of the most celebrated calculations in modern physics and proving that Bekenstein was right all along. Hawking's calculations showed that when you apply quantum field theory to the curved spacetime around a black hole, it indeed has a temperature, now called the Hawking temperature, and it indeed emits radiation. This completed the picture, establishing the four laws of black hole thermodynamics, which perfectly mirror the classic laws of thermodynamics for ordinary matter. The zeroth law states that the surface gravity on the event horizon is constant, analogous to temperature being constant in a system in thermal equilibrium. The first law relates the change in a black hole's mass to changes in its horizon area, spin, and charge, just as the classic first law relates a change in energy to work and heat. The second law, the most famous, states that the total area of all event horizons can never decrease. This is the black hole version of entropy, always increasing. If two black holes merge, the area of the new, larger event horizon is always greater than the sum of the areas of the original two. The third law states that it's impossible to reduce a black hole's surface gravity to zero through any finite process, just as you can never reach absolute zero in a lab. The implications of this are staggering. The formula for a black hole's entropy is breathtaking in its simplicity and its enormity. It is 1/4 of the area of its event horizon measured in Planck units. The Planck area is inconceivably small, about 10 to the -70th square meters. This means a single stellar mass black hole has an entropy value of about 10 to the power of 78. To grasp how astronomically huge that number is, consider that the entropy of all the stars, gas, and particles in the entire observable universe is only about 10 to the power of 104. A single black hole, an object we think of as simple, contains 1,000,000 times more entropy than everything else in the universe combined. It is the ultimate reservoir of cosmic disorder, the most efficient container of information and chaos that physical reality allows. This discovery of black hole entropy forged an unbreakable link between three seemingly separate domains: gravity, described by general relativity; thermodynamics, the science of heat and energy; and quantum mechanics, the science of the very small. The fact that entropy is proportional to area, not volume, was the first strong hint of the holographic principle, the radical idea that all the information describing a three-dimensional volume of space might be encoded on its two-dimensional boundary. A black hole's event horizon is like the ultimate hard drive, and its entropy tells us its maximum information storage capacity. Each tiny plank-sized square on the horizon can hold just a single bit of information, a 1 or a 0. The entire history of everything that ever fell in is painted onto this vast two-dimensional surface, preserved in the most efficient code imaginable. This deep connection between information, gravity, and thermodynamics is now one of the most active and exciting frontiers in physics, guiding us toward a theory of quantum gravity and revealing that even in the deepest darkness, the universe is keeping a perfect, if deeply hidden, account of everything that has ever been. While we often picture a single, solitary titan reigning at the center of a galaxy, the universe is far more dynamic and violent, with galaxies frequently colliding and merging in a slow-motion cosmic dance. This brings us to a spectacular and complex phenomenon: supermassive black hole binaries, where two of these gravitational behemoths are locked in a mutual orbit, destined for an eventual collision of unimaginable scale. These incredible pairings are the direct and inevitable result of galactic mergers. When two galaxies are drawn together by gravity, their stars and dark matter halos gradually intermingle over billions of years. But their supermassive black holes, each the anchor of its former galaxy, face a different fate. Initially, they will reside in the newly formed galactic core, separated by thousands of light years. As they interact with the surrounding stars and gas, they lose orbital energy through a process called dynamical friction, slowly sinking toward the common center of gravity. Eventually, they close the distance enough to form a gravitationally bound pair, a binary system where these two invisible monsters begin to orbit one another. One of the most fascinating and well-studied examples of such a system is a blazar known as OJ-287, located about 3.5 billion light-years away. Observers noticed that this object would undergo dramatic, predictable outbursts of brightness roughly every 12 years. The explanation for this cosmic clock turned out to be a stunning binary black hole dynamic. The system is thought to be dominated by a truly enormous primary black hole with a mass of over 18 billion suns. Orbiting it is a smaller, yet still supermassive, companion weighing in at 150 million solar masses. The smaller black hole's orbit is highly elliptical, meaning it's not a perfect circle but a stretched-out oval. This is the key to the predictable flares. As the smaller black hole plunges through the primary's accretion disk on its closest approach, it violently shocks the superheated gas, causing two tremendous bursts of radiation, a smaller one as it enters the disk and a larger, more brilliant one as it exits. The timing of these flares is so precise that it allows astronomers to test general relativity with remarkable accuracy, as the orbit itself gradually precesses due to the intense curvature of spacetime around the pair. The final act for any supermassive black hole binary is one of the most energetic events conceivable, a merger. As the two black holes spiral ever closer, they radiate their orbital energy away in the form of gravitational waves, those ripples in the fabric of spacetime. This loss of energy tightens their orbit, increasing their speed and the amplitude of the gravitational waves in a runaway process known as in-spiral. In the last few minutes before collision, they can reach speeds approaching half the speed of light, whirling around each other hundreds of times per second. The frequency of the gravitational waves they emit rises into a chirp detectable by future space-based observatories. When they finally merge, the resulting cataclysm is beyond comprehension. In a fraction of a second, an amount of energy equivalent to several times the mass of our Sun is converted into gravitational waves and blasted across the universe, briefly outshining all the stars and galaxies combined in gravitational power. The newly formed single black hole is initially a lopsided, mangled object, ringing like a struck bell as it settles into a stable, spherical shape. This ring-down phase also produces gravitational waves at specific frequencies, which will tell us about the mass and spin of the final product. Observing these mergers will be the ultimate test of Einstein's theory under the most extreme conditions, and will allow us to map the population of these binary systems throughout cosmic history, revealing the story of how galaxies built themselves up through collisions and how their dark hearts eventually found each other to create even greater giants. Their influence extends far beyond their home galaxies, weaving a thread of cause and effect throughout the very largest structures in existence. To truly grasp their cosmic role, we need to pull back our perspective to the grandest scale possible, viewing the universe as a vast, interconnected web of dark matter filaments, with galaxies and clusters glowing like dewdrops at the intersections of these invisible strands. This is the cosmic web, and black holes are not just passive residents, they are powerful architects that help shape its very form. This process of large-scale construction is driven by their most powerful tool, feedback. We've seen how a black hole's jets and radiation can regulate star formation within its own galaxy, but that energy doesn't just stop at the galactic border. When a quasar erupts or a jet launches from a supermassive black hole, that colossal outpouring of energy plows into the intergalactic medium, the incredibly thin, superheated gas that fills the space between galaxies. This isn't a gentle nudge, it's a cosmic tsunami. The energy heats this diffuse gas, preventing it from cooling down and falling inward under gravity to feed the galaxy and form new stars. On a colossal scale, this means that the most active black holes can effectively shut down star formation, not just in their own galaxy, but across entire galaxy clusters, influencing the growth of hundreds or even thousands of galaxies at once. The consequences of this feedback ripple through the cosmic web in fascinating ways. By heating the gas within and around galaxy clusters, black holes effectively dictate where future generations of stars can and cannot form. This process helps explain why we don't see stars forming in the vast, empty voids between the web's filaments. The black holes in the denser regions have helped keep that gas far too hot and energetic to ever collapse. It also influences how galaxies themselves are distributed. Simulations of the universe's evolution that include black hole feedback produce a cosmic web that matches our observations almost perfectly. The clusters, the filaments, the voids all fall into place. When scientists run the same simulations without incorporating this black hole influence, the results are wildly off. The models create far too many massive, bright galaxies, and the gas in clusters cools too efficiently, creating a universe that looks nothing like our own. This tells us that the energetic outbursts from these dark hearts are not a minor side effect. They are an essential ingredient in the recipe for our universe's large-scale structure. Observational evidence for this profound influence is written across the sky. In many massive galaxy clusters, the central supermassive black hole has blown enormous bubbles of radio-emitting plasma into the surrounding hot gas. These bubbles, which can be millions of light years across, are the fossilized remnants of past jet eruptions. They push the cluster gas aside, sculpting vast cavities and creating ripples that travel through the intergalactic medium like sound waves in a pond. These ripples help to keep the gas hot, preventing widespread cooling and acting as a long-term thermostat for the entire cluster. By studying these imprints, astronomers can read the history of a black hole's activity and see firsthand how its violent outbursts, which last for millions of years, can shape its environment for billions of years to come. The black hole's brief eruptions create echoes that resonate for eons, governing the growth of structures on the very largest scales and proving that even the darkest objects are indispensable to the universe's luminous design. While the reality of black holes is strange enough, the equations of general relativity open doors to possibilities that are even more fantastical, theoretical realms that challenge our very understanding of causality and connectivity in the cosmos. These are not just black holes, but potential gateways, cosmic shortcuts, and even the theoretical opposites of the ultimate cosmic trap. Perhaps the most famous of these exotic ideas is the wormhole, formerly known as an Einstein-Rosen bridge. The mathematics of general relativity allows for the existence of a tunnel-like structure that could create a shortcut through spacetime, connecting two distant points or even two different universes. Imagine spacetime as a vast, flat piece of paper with 2 points marked far apart. The normal journey between them is a long line across the paper. But if you could fold the paper so those 2 points touch, a wormhole would be like a pencil poking through the fold, creating an instant bridge. The entrance to one of these tunnels could look very much like a black hole, a point of no return. But theoretically, if the tunnel was stabilized and traversable, something could pass through it and emerge from the other end, a white hole, in a different location or time. This brings us to the concept of the white hole, the hypothetical opposite of a black hole. If a black hole is a region of space where nothing can escape, a white hole would be a region where nothing can enter. It would violently expel all matter and energy, a fountain of cosmic material erupting from a singularity. While mathematically permissible as a time-reversed black hole in the equations of general relativity, white holes are considered supremely unlikely to exist in nature. They violate the second law of thermodynamics, representing a decrease in entropy, and there is no known physical process that could create one. Most physicists view them as fascinating mathematical curiosities rather than real astrophysical objects. A more plausible, yet still highly speculative, exotic object is the Kerr black hole with a traversable interior. Most black holes we discuss are modeled as Schwarzschild black holes eternally collapsing, static objects with a terrifying singularity at their center, a point of infinite density where the laws of physics break down. However, the solution for a rotating black hole, described by mathematician Roy Kerr, is far more complex and intriguing. A Kerr black hole does not contain a point singularity. Instead, its rotation flattens the singularity into a ring. This ring singularity, according to the math, might not have infinite density, and it's theorized that the extreme centrifugal forces could keep it open. This ring structure leads to a breathtaking possibility. The equations suggest that if you were to somehow pass through the ring singularity, you might not be crushed into nothingness. You could potentially enter a region of negatively curved spacetime and exit into a different universe or a different part of our own. You would have found a naturally occurring, albeit incredibly dangerous, wormhole at the heart of a spinning black hole. However, this theoretical pathway is almost certainly impassable. The interior of a Kerr black hole is likely filled with lethal radiation, chaotic closed time-like curves that could violate causality and instability. The ring itself might be surrounded by a region of infinite tidal forces called a Cauchy horizon, which would shred any object apart before it could reach the gateway. Furthermore, any matter falling into the black hole would likely collapse the hypothetical tunnel, making it non-traversable. The fundamental question is whether these wonders are anything more than mathematical phantoms. Do the solutions in Einstein's equations that allow for wormholes and white holes correspond to physical reality, or are they artifacts that disappear when we apply a more complete theory, such as quantum gravity? Most of these exotic structures require the existence of exotic matter, a theoretical substance with negative energy density that would exert a repulsive gravitational force. This exotic matter would be needed to prop open the throat of a wormhole, preventing it from pinching off instantaneously. While tiny amounts of negative energy density might be possible through quantum effects like the Casimir vacuum, the quantities needed to stabilize a macroscopic wormhole are astronomical, and MOY Chinese letter known energy conditions, the very rules that prevent things like time travel and perpetual motion machines. These exotic theories, while likely beyond our current technological reach, are far from useless. They serve as incredible stress tests for the theory of general relativity itself. By pushing the math to its absolute limits, physicists can explore the boundaries of what is possible within our current understanding of the universe, often revealing deep inconsistencies that point the way toward a more complete theory of quantum gravity. They challenge our intuitions about space, time, and connection, reminding us that the universe described by fundamental physics is far stranger and more wonderful than our everyday experience could ever suggest. But to truly grasp the full picture of these cosmic enigmas, we can't rely on a single way of looking at them. Astronomers have assembled a formidable toolkit, a symphony of instruments working across the entire spectrum of light and even beyond, each designed to listen to a different part of the black hole story. It's like investigating a crime scene with ultraviolet scanners, thermal cameras, and sound detectors. Each tool reveals evidence the others cannot see. For capturing the intense violence of a black hole's feeding habits, nothing beats an X-ray telescope. When matter is torn apart and superheated to millions of degrees in the accretion disk, it doesn't shine in visible light, it screams in high-energy X-rays. Orbiting high above Earth's atmosphere, which blocks these dangerous rays, NASA Chandra X-ray Observatory acts as our premier eye in the X-ray sky. By staring at objects like Cygnus X-1 or the heart of the Phoenix cluster, Chandra maps the seething, tumultuous plasma just outside the event horizon. It measures the Doppler shifts and gravitational redshifts in the ion emission, lines from this whirling gas, allowing scientists to calculate a black hole's spin with incredible precision. It's like being able to tell how fast a top is spinning by listening to the precise pitch of its hum. Without this window into the highest energies, we would be blind to the most dramatic processes powering these cosmic engines. To see the larger structure, especially the colossal jets that can stretch for millions of light years, we turn to the radio part of the spectrum. This is where interferometry comes into play, the technique of linking multiple radio dishes together to act as one gigantic telescope. The Atacama Large Millimeter/Submillimeter Array, or ALMA, situated on a high plateau in Chile, is a masterpiece of this technology. Its dozens of precise antennas work in concert to achieve breathtaking resolution, allowing it to see the magnetic fields that thread through and help launch those powerful jets. ALMA can even peer through the obscuring dust at the centers of galaxies to study the cold gas reservoirs that are waiting to feed the central black hole. And of course, it was a key part of the Global Event Horizon Telescope network that gave us our first unforgettable image of M87's shadow. Radio interferometry doesn't just show us the blaze of the black hole's dinner plate. It shows us the entire table setting and the immense plumes of smoke billowing from the kitchen. And now we stand on the brink of a completely new era of observation, one that doesn't rely on light at all. The Laser Interferometer Space Antenna, or LISA, is a future mission that will open our ears to the universe. Unlike Earth-bound detectors like LIGO, which are limited to hearing the high-frequency chirps of merging stellar mass black holes, LISA will consist of 3 spacecraft flying in a vast triangular formation, trailing Earth in its orbit around the Sun. With arms millions of kilometers long, this space-based observatory will be exquisitely tuned to the low-frequency rumble of the cosmos. It will be able to hear the gravitational wave hum from massive binary black holes in the centers of merging galaxies, listening for years as they spiral ever closer. It will detect the final merger of supermassive black holes, events so energetic they will shake the very fabric of space-time across the entire universe. LISA won't just give us a snapshot, it will provide a continuous soundtrack to the cosmic dance of the largest black holes, from their first approach to their final universe-shaking collision. But for all their immense gravitational power, black holes influence far more than just the space around them. They warp the very fabric of time itself. This brings us to one of the most mind-bending consequences of Einstein's general relativity, a phenomenon known as time dilation. The principle is both simple and utterly profound. Gravity doesn't just bend space, it also slows down time. The stronger the gravitational field, the more time slows relative to a weaker field. A black hole with its unimaginable density creates the most intense gravity well in the universe, and at its precipice, the effect on time is nothing short of spectacular. Imagine a thought experiment with two identical, super-precise clocks. One clock remains far away from any significant source of gravity, perhaps with a distant observer. The other clock is carried on a spacecraft that journeys ever closer to a black hole's event horizon. From the perspective of the distant observer watching through a powerful telescope, something strange begins to happen. As the spacecraft approaches the event horizon, it appears to slow down. Its signals, whether light or radio waves, start to stretch out, their frequency dropping in a dramatic gravitational redshift. The clock on the screen appears to tick slower and slower. As the ship gets infinitesimally close to the event horizon from the outside perspective, its time appears to grind to a near halt. The ship and its clock seem to hover, frozen, for what would effectively be an eternity, never quite crossing the boundary from the vantage point of the universe at large. Now let's shift perspectives to the brave, or perhaps foolhardy, astronaut inside that spacecraft. For them, time continues to pass at a completely normal rate. Their heartbeat, their thoughts, the ticking of the clock on their console, none of it feels any different. They would cross the event horizon without any fanfare, passing that point of no return in a finite amount of their own personal time. The dissonance between these two experiences is absolute and real. It's not an illusion, it's a fundamental property of the universe. The astronaut's journey into the black hole might take just a few hours from their own frame of reference, while outside, billions of years could have passed. The universe would have aged eons, stars would have been born and died, and civilizations could have risen and fallen, all in the time it took for the astronaut to make their final plunge. This isn't just theoretical. We have direct, measurable proof of time dilation right here in our own solar system, though on a much smaller scale. The Global Positioning System, or GPS, is a network of satellites orbiting Earth. Because they are farther from Earth's center of mass than we are, they experience slightly less gravity. According to general relativity, their clocks should run faster than identical clocks on the surface. If this effect weren't constantly corrected for, the GPS system would accumulate errors of several kilometers per day, rendering it useless. Engineers must deliberately program the satellite clocks to tick slower before launch, knowing that the weaker gravity in orbit will speed them up to match our clocks on the ground. This is a practical, everyday application of gravitational time dilation, a tiny whisper of the overwhelming temporal distortion that occurs at the edge of a black hole. The implications of extreme time dilation stretch our imagination to its breaking point. It presents a fascinating, if purely hypothetical, form of time travel into the future. An astronaut could, in theory, use a black hole as a time machine, by taking a path that brings them very close to the event horizon and then returning to their starting point, a maneuver requiring impossible amounts of energy and technology we can scarcely dream of. They could return to find that far more time had passed for everyone else than had passed for them. They would have effectively jumped thousands or millions of years into the future. Of course, this is a one-way trip. There is no return to the past. But it illustrates how these cosmic monsters don't just trap matter and light. They ensnare time itself, creating realms where the universal clock ticks at a rate that is utterly alien to the rest of the cosmos. Yet, even as we catalogue these record-breaking champions, a profound question emerges from the data. What do these incomprehensible sizes tell us about the ultimate upper limits of black hole growth? Is there a point where a black hole simply cannot get any bigger? Theoretically, the only true limit is the availability of mass to consume. A black hole could, in principle, keep growing forever as long as it has a steady supply of gas, stars, and other black holes to merge with. But the universe itself imposes practical constraints. The most significant limiting factor is its own incredible power. As a black hole feasts and its accretion disk shines with the fury of a quasar, the radiation pressure from that brilliance pushes back against the infalling matter, effectively blowing its own food supply away. This self-regulating mechanism, known as the Eddington limit, acts as a cosmic throttle, preventing the black hole from consuming material too quickly and setting a maximum rate for stable growth. Furthermore, a supermassive black hole's immense gravity and energetic jets heat the surrounding gas in its host galaxy and beyond, creating a vast hot bubble that prevents further cooling and star formation, ultimately starving itself of future fuel. The existence of these multi-billion solar mass titans so early in the universe's history suggests they must have experienced periods of super-Eddington accretion, somehow breaking through this limit during a special era when gas was unimaginably plentiful and could fall in at a rate that overwhelmed the radiation pressure. These cosmic giants are not just record holders, they are boundary markers showing us the absolute extremes of physics and revealing a universe that, in its youth, operated under a different, more violent set of rules to build its most magnificent monsters. Perhaps the most persistent and gripping image of a black hole is that of an unstoppable cosmic vacuum cleaner roaming through the galaxy and devouring everything in its path. This makes for fantastic science fiction, but it's a dramatic oversimplification of how gravity actually works. A black hole's gravity is no different in nature from the gravity of a star or a planet. It simply operates from a point of incredible density. Its power to suck things in is no more potent than that of any other object of the same mass. If you were to magically replace our sun with a black hole of exactly the same mass, a chilling darkness would fall over Earth, but our planet's orbit would remain completely unchanged. We would continue to trace the same elliptical path through space, not because we are resisting some irresistible pull, but because the gravitational source at the center of our solar system hasn't changed in strength, only in form. The danger lies not in a black hole's ability to pull from afar, but in venturing too close to its event horizon, where the gradient of its gravity, the difference in pull from your head to your toes, becomes the real killer. This leads to another widespread myth, the idea that black holes are inherently rare, exotic anomalies. The reality is that they are likely a fundamental and common feature of the cosmos. Current astronomical theories suggest that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its core, but the story doesn't end there. Stellar mass black holes, the remnants of massive stars, are thought to be incredibly numerous. Our galaxy alone could be home to 100 million of these dark remnants, silently orbiting among the stars. The universe isn't sparsely dotted with these objects. It's likely teeming with them, a hidden population of gravitational ghosts from a billion stellar deaths. Their prevalence isn't a sign of cosmic danger, but a natural consequence of the life cycle of the most massive stars. another common misconception concerns their formation. The standard image is a single massive star exploding in a supernova and its core collapsing inward. While this is one valid path, it's not the only one. We now know that many stellar mass black holes are born not from a single star's death, but from the merger of two dense stellar remnants in a binary system, like two neutron stars colliding. More mysteriously, the seeds of the supermassive giants at the centers of galaxies may have formed through entirely different processes in the early universe, such as the direct collapse of enormous primordial gas clouds, bypassing the star stage entirely. The origin story of black holes is not a single, simple tale, but a complex anthology of creation myths, each dependent on the environment and the era of the cosmos. Many people also envision the interior of a black hole as a place of chaotic, constant destruction, a raging furnace where matter is endlessly annihilated. This, too, is a misunderstanding rooted in our classical view. From the perspective of an outside observer, due to the extreme effects of gravitational time dilation, matter that falls into a black hole never actually appears to cross the event horizon. It seems to slow down, redden, and fade from view, frozen in time at the edge. From the perspective of the matter itself, it would cross the horizon and continue inward, but the modern theoretical view, informed by quantum mechanics, suggests that information about that matter isn't necessarily destroyed. Concepts like the holographic principle propose that the information is encoded on the event horizon's surface, and the black hole's interior might be far more complex and structured than a simple crushing singularity. The true nature of what happens inside remains one of physics' greatest mysteries, but it is almost certainly not the simplistic blender of doom we often imagine. Finally, there's the pervasive idea that black holes are only relevant to the most abstract theoretical physicists. The truth is, their study has profoundly practical implications that touch on the fundamental laws governing our entire reality. The quest to resolve the black hole information paradox, for instance, is forcing us to reconcile Einstein's theory of general relativity with quantum mechanics, a unification that would constitute a theory of everything. Understanding how black holes emit Hawking radiation and evaporate over eons gives us deep insights into thermodynamics and the nature of entropy. Even our GPS satellites must account for the tiny time dilation effects predicted by the same theory that describes black holes, or they would be useless within minutes. Far from being irrelevant cosmic curiosities, black holes are extreme natural laboratories, pressing against the boundaries of our knowledge and compelling us to refine our understanding of the universe, from the infinitesimally small to the impossibly large. For all the staggering discoveries we've made about these cosmic giants, from their immense shadows to the gravitational waves they create, the truth is we are still only at the beginning of this journey. The future of black hole research promises to be even more revolutionary, propelled by a new generation of telescopes and supercomputers that will allow us to peer further back in time and listen more closely to the whispers of space-time than ever before. One of the most eagerly awaited tools is the James Webb Space Telescope, which is already transforming our view of the early universe. Its unparalleled infrared sensitivity allows it to look back to an era known as cosmic dawn, when the very first stars and galaxies were beginning to ignite. A key mission for Webb is to hunt for the seeds of supermassive black holes in this primordial darkness. By studying the most distant quasars, it can analyze the composition of the gas in their host galaxies, searching for the telltale signatures that distinguish between different formation theories. Did these early black holes form from the collapse of the first massive population 3 stars? Or does Webb's data point toward the direct collapse of primordial gas clouds, creating those massive seeds we need to explain the existence of billion solar mass monsters in the universe's infancy? Webb acts as a cosmic archaeologist, sifting through the light of the earliest epochs to uncover the birth certificates of the universe's first dark giants. While Webb observes the light from early black holes, a future mission will listen for their motion. The Laser Interferometer Space Antenna, or LISA, represents a monumental leap in gravitational wave astronomy. Unlike its Earth-bound predecessors LIGO and Virgo, which are tuned to the high-frequency chirps of merging stellar mass black holes, LISA will be a space-based observatory consisting of 3 spacecraft flying in a perfect triangular formation millions of kilometers apart. This gigantic instrument will be exquisitely sensitive to the low-frequency rumble of the cosmos. It will be able to detect the gravitational wave hum emitted by binary supermassive black holes as they slowly spiral toward each other over millions of years. LISA won't just hear the final collision. It will provide a continuous soundtrack to the entire cosmic dance, from their first approach to their eventual universe-shaking merger. This will allow us to take a full census of these binary systems, understanding how often galaxies merge and how their central black holes find each other, ultimately mapping the growth history of the largest black holes across cosmic time. On the theoretical front, the quest continues through increasingly sophisticated supercomputer simulations. These are not simple animations. They are complex digital universes where physicists program in all the known laws of physics, gravity, magnetohydrodynamics, thermodynamics, and then set them in motion to see what emerges. The latest simulations are now beginning to incorporate the elusive effects of black hole feedback with stunning detail, showing how jets and radiation actually interact with the surrounding gas on both galactic and intergalactic scales. They are creating virtual laboratories to test the holographic principle and other potential resolutions to the information paradox. Furthermore, as we gather more data from observatories like Webb and LISA, these simulations will be crucial for interpreting the results, allowing us to run countless virtual universes with different starting parameters to see which one best matches the real cosmos we observe. The ultimate goal unifying all these efforts is the pursuit of a theory of quantum gravity, a framework that can seamlessly marry the large-scale warping of spacetime described by Einstein with the tiny, probabilistic world of quantum mechanics. Black holes are the perfect testing ground for this because they are the simplest objects in the universe, defined by just mass, spin, and charge, yet they create conditions where both gravity and quantum effects are paramount. By studying the Hawking radiation of an evaporating black hole or the quantum fluctuations at the event horizon, physicists hope to find the fingerprints of a deeper reality. The data from these future observatories might provide the crucial clues, the unexpected measurements that don't quite fit our current models, forcing a revolution in our understanding and finally granting us a glimpse of the laws that govern the universe at the moment of its birth. The future of black hole research is not just about finding bigger black holes. It's about using these ultimate natural laboratories to answer the most fundamental questions of all. Yet after exploring 30 astonishing facts about their scale, power, and physics, we are left with something even more profound than data, a deep, resonating sense of awe that transcends science and brushes against the philosophical. These cosmic giants are not just physical phenomena, they are powerful mirrors reflecting our deepest questions about reality, time, and our own fragile existence in this vast universe. Consider for a moment our relationship with time. Black holes literally warp it, creating realms where a single hour near the event horizon could equal millennia elsewhere. This isn't just a mathematical curiosity, it fundamentally challenges our human perception of time as a steady, universal constant. We experience our lives as a linear progression, a one-way journey from birth to death. But black holes show us that time is malleable, a fluid dimension woven into the fabric of space itself. They humble us, revealing that our entire history, every empire built, every story told, every life lived, is but a fleeting blink in the eye of a cosmic entity where time can stretch and compress to an almost meaningless degree. They force us to confront the fact that our experience of reality is not the only one, and perhaps not even the most true. This leads to even deeper existential questions. The black hole information paradox, for instance, is more than a technical puzzle for physicists. It touches on the very nature of existence and identity. If an object or a person falls into a black hole, is the information that defined them truly lost forever? This challenges the core principle that the universe is knowable and predictable, that cause and effect are sacred. It makes us wonder about the permanence of things and the very nature of what it means to be. Are we more than just the sum of our particles? If all the information that made a star can be seemingly erased, what does that say about the legacy of our own, infinitely more complex lives? Black holes, in their utter darkness, push us to illuminate the most fundamental questions of what reality is made of. Their cultural impact is a testament to this power to captivate and terrify. They are the ultimate unknown, and humanity has always spun stories around the void. In film, from the terrifying reality-bending journey in Interstellar to the ominous threat in Event Horizon, black holes serve as perfect metaphors for the unknown, for temptation, for danger that is both intellectual and visceral. In literature, they are gateways, prisons, and guards. They represent the ultimate challenge to exploration, the final frontier where the known laws of physics break down and anything becomes possible. This cultural permeation shows that black holes do more than just pull on matter. They pull on our imagination, becoming symbols for our greatest hopes and deepest fears about the cosmos. Ultimately, the study of black holes is a profoundly human endeavor. It is a pursuit driven by an insatiable curiosity to understand the universe and, in doing so, to understand ourselves. Every observation, every theoretical breakthrough, is a testament to our species' unique ability to look into the abyss and not only wonder what is there, but to devise ingenious ways to find out. We use the laws of physics as a lantern, shining a light into the darkest corners of creation, and in that light we see our own reflection. We are tiny, fragile creatures on a pale blue dot, and yet we can measure the spin of a monster 55 million light-years away. We can hear the echoes of collisions that happened before our planet even formed. This incredible power of comprehension gives our existence a beautiful significance. Black holes teach us that we are not just passive inhabitants of the universe, but active participants in its unfolding story, capable of seeking, and perhaps one day finding, answers to the biggest questions of all. From the silent, frozen behemoth at the heart of our own Milky Way to the roaring, hyperluminous quasars that outshine entire galaxies, our journey through 30 facts has revealed black holes not as simple vacuum cleaners of space, but as the universe's most dynamic and influential architects. We've witnessed their birth in the cataclysmic deaths of massive stars and pondered their potential origins as primordial seeds from the dawn of time. We've seen how they grow, not just by steady accretion, but through violent mergers that shake the very fabric of space-time, sending out gravitational wave chirps that we can now detect from over 1 billion light-years away. Their power is expressed in relativistic jets that sculpt entire galaxy clusters, and in brilliant flares from stellar tidal disruptions that briefly outshine every star in their host galaxy. We've grappled with the mind-bending physics they impose, from the time-stretching effects at their event horizons to the quantum mechanical puzzle of Hawking radiation and the terrifying information paradox. They challenge our very understanding of reality, suggesting that all we see might be a holographic projection and that the three-dimensional world we experience could be an illusion. They are the ultimate paradoxes, objects of stunning simplicity, describable by only mass, spin, and charge, yet containing more entropy and disorder than everything else in the observable universe combined. They are both destroyers and creators, capable of shutting down star formation across vast distances, while also potentially seeding new generations of stars through complex feedback loops. They are the darkness that gives form to the light, the gravitational anchors around which galaxies spin, and the engines that have shaped the large-scale structure of the entire cosmic web. This exploration is far from over. Every new observation, from the Event Horizon Telescope to the James Webb Space Telescope, peels back another layer of the mystery, revealing deeper questions and more astonishing possibilities. The universe is a place of magnificent scale and profound wonder, and these cosmic titans are its most compelling evidence. We want to hear from you which of these 30 facts reshaped your understanding of the cosmos the most. Was it the sheer immensity of Ton 618, the dynamic feedback of the Phoenix cluster, or the philosophical implications of the holographic principle? Share your thoughts in the comments below, and if you enjoyed this voyage to the edge of reality, make sure to subscribe and hit the notification bell so you don't miss our next journey into the deepest mysteries of space.